Good afternoon, everyone. I'm going to start us off today by demoing exercise 10. Exercise 10, we've got this massive pulley with the given mass and given radius. And we've got a pair of tension forces applied at different points on the pulley. And we want to find the angular acceleration of the pulley. So for this, we're going to need to use Newton's second law for rotations, which tells us that our net torque is equal to our moment of inertia times our angular acceleration. Oh, I should probably add my axes on here. We'll just do the usual z out, x to the right, y up. Right, so there are two steps here. We're going to need to find the net torque, and we're going to need to find the moment of inertia. And from this information, we'll then be able to solve Newton's second law for alpha. Our net torque is going to be the sum of all of the torques acting on the pulley, and each of the torques will be produced by one of the associated forces, one of the two tension forces. So let's take this one over on the left first. The torque associated with 12 Newton force, we do R cross F. So we'll have the magnitude of R, where R measures from our axis of rotation out to the point where the force is applied. So that'll just be the full radius of the pulley, times the magnitude of F, the 12 newtons, times the sine of the angle between the two vectors, and all of our forces here are acting tangentially to the pulley. So the angle between our R and F will be 90 degrees. So this just becomes 1. For the direction of the torque, we use the right-hand rule. We put our fingers along R and then curl in the direction of F, and our thumb points out of the page, so the 12 Newton torque is rotating us in the positive z-hat direction. For the 10 Newton torque, our R is the same as before. It's the radius of the pulley, the 30 centimeters. The force now is 10 newtons, and the angle will once again be 90 degrees because R goes out radially and our force is applied tangentially. So we again have sine of 90 degrees, or just 1. For the direction, we have R going up and to the right, then our force going down to the right. So our thumb points into the page, that's our negative z direction, which is sensible enough because our two forces appear to be rotating us in opposite directions. So our net torque is the sum of the two torques we just found. And we now punch these into our calculator. So you've got 30 centimeters times 12 newtons, which will give us 3.6 Newton meters from the 12 Newton torque. And then 3 Newton meters from the 10 Newton torque. which gives us a net torque of 0.6 Newton meters in the positive z direction. Right, so we've got our net torque. Now we need to find the moment of inertia. We have a solid disk, and we're rotating about an axis that goes through the center of mass of the disk. So this is one that we have in our table. The moment of inertia for such a disk is 1/2 times the mass times the radius of the disk squared. Again, we punch this into our calculator. And be careful of the fact that you have centimeters being squared there. You're going to want to convert that into meters. Careful with your conversion factor. You wind up with, just a moment. So I've got 0.036 kilogram meters squared. Now for my angular acceleration, I go back to Newton's second law, solve the equation for alpha, and plug in the net torque and the moment of inertia, which we just found. So for the magnitude, I've got 0.6 Newton meters over 0.036 kilogram meters squared. Gives me just about 16.7 per second squared. And my direction is the direction of the torque. That's positive z hat. Just like your acceleration always points in the same direction as your net force, your angular acceleration will always point in the same direction as your net torque. Right, so we've got our answer. This problem asked us to put a few things together. We needed to know how to turn forces into torques, needed to be able to do a vector sum of those torques to get the net torque, needed to know the moment of inertia for our solid disk, and needed to put the moment of inertia and the net torque together to solve for the angular acceleration. I hope this has been helpful. Good luck with the rest of the problems, and if you need any further advice, I'll be around this afternoon.